All right. So today I think I am going to dive deep into this question of why a positive definite matrix has a Kolosky decomposition. What is Kolosky decomposition? You can write this matrix as product of R transpose R. R is a lower triangular matrix. Sorry, R is a upper triangular matrix. R transpose becomes a lower triangular matrix. R is of course equal to R transpose, and this is only possible if the matrix is positive definite, or at the most you can have it a positive. To be very honest, I think you can permit positive semi-definite matrix with rank n minus 1. So, but let's not get into that much of technicality. We'll say that if the matrix is positive definite, so possible if A is positive semi-definite and rank is of the matrix is greater than or equal to n minus 1. Of course, once I have, if it becomes rank n and positive, then it automatically implies this, and positive semi-definiteness automatically implies that it is positive definite, because I think I'll come to this as I expand it. If it is rank n minus 1, then basically what it means is that there is some vector z not equal to 0, which is which makes 0 as its eigenvalue. But if it becomes rank n, then ax equal to 0 is only possible if x is equal to 0. So therefore there is no 0 eigenvalue now. So therefore the matrix will become positive definite. We'll come to this. I think you have got a reasonably good intuition of it, but I want to go into it in a slightly systematic systematic way. So first of all, let me recall what do you mean by linear combination of vectors. You have a1, a2 up to say am vectors, aam. Each of these vectors is, let's say, from Rn, and I look at linear combination means I multiply these vectors by scalar and add them. Now this is nothing but what I have got here is nothing but the linear combination of x1 to, sorry, of a1 to am vectors. Sometimes I put the arrow to emphasize that it is vector, and my x1, x2 to xmr, these are all scalars which I have written here as a, this collection I have written here as a vector. The reason I wrote it is like it was like this is that I can group these vectors in a matrix a1, a2 to am in a matrix form, and hence a linear combination will then become, and this I will call it as a x vector. Then the linear combination is nothing but a times of x. So sometimes if you recall, we have looked at it as a linear transformation. Now we are looking at it as a linear combination. So matrices provide us a very compact notation and helps to look at many things from this nice, simple and compact notation. Now there are two concepts here that I want to bring out. One is linear dependence of vectors, or alternately linear independence of vectors. Now, what I mean by linear dependence of vectors is that, suppose, let's say I have three vectors, okay, a1, a1, A2, A3. And let's say A3 can be written as 2 times of A1 minus of A2. If such is the case, I will say that A3 is linearly dependent on A1 and A2. Now, if such is the case, you can see that A1, A2, A3, which I put in the matrix forms, times 2 minus 1 and A3 I am going to take it to the right side. So this will also become minus 1 multiplication factor. Minus 1 will become equal to 0. So basically what it means is that in a linearly dependent set of vectors, every vector in that set can be expressed as some linear combination, non-trivial linear combination of the remaining vectors. So we say that a set of vectors is linearly dependent if we say that it is linearly dependent if their linear combination can be taken to 0 in such a way that all xi's are not 0. If that is the way you can do it, then you can say that it represents these vectors are linearly dependent. In other words, Ax is equal to 0 because linear combination can always be written as A times of x. So Ax equal to 0 has has a non-trivial solution. And what does that solution non-trivial means? X not equal to 0. Which is the trivial solution? The trivial solution is x equal to 0. This will always make the product Ax go to 0. So when x is not equal to 0 and the product Ax can be taken to 0, then we say that it is a non-trivial combination. So we say that a set of vectors, a set of vectors a1, a2 to am, each of the ai coming from Rn are linearly independent if their linear combination going to 0 is possible if and only if the corresponding scalars go to 0. Otherwise, if this is not the case, then there is some non-trivial vector x which will take it this linear combination to 0. So therefore, otherwise, in which case it is linearly dependent. Okay. Now let's come back to Rn. We say that dimension of Rn is n. What does that mean? Actually, that means that vector space Rn can be derived from n linearly independent vectors, which, as the name suggests, constitutes its basis. So, in other words, what I am saying is basis is that minimal set of linearly independent vectors that generates a given vector space. So, for example, again, if I come to Rn, then the first vector of the identity matrix, the second vector of the identity matrix, and so on up to the nth vector of the identity matrix. This is that minimal linear set. This is that minimum linear set, right? Which will generate any vector, which will generate any vector x1, x2 to en xn. It will generate any vector alpha 1, alpha 2 to alpha n in the vector space. All you have to do is choose x1 is equal to alpha 1, x2 is equal to alpha 2, xn is equal to alpha n. So this statement that a set of vectors generate a vector space is equivalently stated as the vectors, whatever that set be, in my case e1, e2 to en, span the vector space. In my case, what is the vector space? The Rn. If this spanning set of vectors is a minimal set, then it is called a basis. And obviously, it has to be, obviously, in a basis, the vectors should be linearly independent. Look at this. Let me take an example of two dimension 1 0, 0 1, 1 1. Obviously, this spans R2. This set of vectors spans R2. But is it minimal? Remove any one of them, doesn't matter which one, third one, second one, or first one, any one. Remove any one, vector, and you still have got a spanning set. You still have got a spanning set. Now, if you try to remove, any further one vector out of it, remove any one, further remove any one, and will it span R2 after that? Further, if I remove a vector from here, say 1 0 or 0 1. So 1 0, suppose I removed, then I get 0 1. Now this does not span R2, is it not? It no more spans R2. So therefore, this minimal 2 set is the one which spans R2, or 1 0 1 1 also spans R2, but you remove another one vector out of here, it no more spans R2. So therefore, this sets constitute the basis. And the basis is, how is a basis obtained? By first taking a spanning set and then filtering out or removing linearly dependent vectors from it, and then whatever minimal set that you get is called the basis. Now, two things very clear from above example. Basis is not unique. I have here itself I have given you two bases for R2, like 1 1 0 0 1 1 0 and 1 1. So therefore basis is not unique, number one. Number two, number of vectors in a basis are identical. And how do you argue this out? Suppose they are not identical, then look at the basis which has a smaller set of number of vectors. Now, since it is a basis, it generates all the vectors in the vector space. In particular, it generates that set which is having larger the other spanning set which you were thinking to be basis, which had larger number of vectors. So therefore, that no more can be basis. It has redundant vectors in it. Therefore, the dimensionality of the basis is always the same. Hence, number of vectors in a basis is called the dimension of the vector space. In Rn case, it is obviously n, right? Because all the identity metric generate, they are the basis of Rn, trivial basis of Rn, and hence the dimensionality of Rn is n. Okay, now when I organize these vectors in basis, no, I'm sorry, when I organize these vectors in matrix, then I will make a count what is the maximal set of linearly independent vectors, okay, in A. If if A1 to A1, AM are all linearly independent, all of them are linearly independent, then I will say, okay, then I will say rank of A is M. In other words, rank is defined as the number of linearly independent vectors in A, corresponding to the, of course, the maximal. I'll make this definition more precise as I go further. I think you have but basically got the idea that I'm looking at the maximal set of linearly independent vectors in A, in this columns of this matrix A, and that number I am calling it as rank. If you want, you can call it also as column rank. If you call that as column rank, then you will also have to define something called row rank, which is what? The number of the maximal set, cardinality of the maximal set of linearly independent rows of A. Now it turns out non-trivial, but it turns out by linear algebra, important theorem of linear algebra, that column rank is equal to row rank, and hence we just use one terminology called rank of a matrix. So what is the rank of the matrix? Rank of the matrix is defined as the number of vectors in the maximal linearly independent set of either rows or columns of A. Okay. So when I say a n cross n matrix, say a 5 cross 5 matrix A has rank 5, then what is the implication? The implication is all columns are linearly independent and all rows are linearly independent. If I say A 5 cross 5 has rank 3, then what does it means? At max means the maximal set of linearly independent columns has dimensionality 3. The maximal set of linearly independent columns or rows has cardinality 3. So therefore it has rank of 3. Now this rank, now it is not necessary that the matrix be square when you are talking of rank. For example, if I say a 5 cross 3 matrix, then it can at most have 3 linearly independent columns. So rank of A could be 3. More correctly, the rank of A matrix will be less than or equal to 3. So in general, if A is a M cross N matrix, rank of A will be less than or equal to minimum of M comma N. Is that clear? This is what we usually say, the rank of matrix is less than or equal to M comma N. Now, once you have come this far, you can now associate with a matrix A, you can associate now with a matrix A a range space and a null space. Both of these are vector spaces. If A is a M cross N matrix, range space is a subset of Rm or a subspace of Rm, and null space is a subspace of Rn. If the matrix is square, then both are subspaces of Rn. Now, what is a range space? Okay. So these are very important questions when you look at linearly constrained optimization problem, which I will be looking at very soon. So what is a range space? Simple, very simple definition. Set of all vectors y, or I like y, which can be expressed as a times of x coming from Rn, constitute the range space of A. Constitute the range space of A. So whenever you solve a linear system of equations Ax equal to B, and if it has a solution, then B has to be in the range space of A. Okay, why is it called a vector space? When I say range space, I imply that range space is a vector space, and I said earlier that it is a subspace of range space is a subspace of Rm. So why do I say that it is a subspace of Rm? First of all, look at the dimensionality. Look at the dimensionality. Ax is a vector in Rm. So therefore, if there is any subspace, it will be of Rm only. So only thing now I need to show is that it is a subspace. So assume that you have two vectors in the Rm. So I have y1 coming from Rm from the range space, so-called range space. We we are verifying it now, and another y2 coming from the range space. Then it means that y1 can be written as a times of x1 and y2 can be written as a times of x2. Then only they will come from that range set or range space. Now look at any linear combination alpha 1 y1 plus alpha 2 y2, which is same as alpha 1 ax1 plus alpha 2 ax2, which is same as a times alpha 1 x1 plus alpha 2 x2. But then the moment I am able to express it as a times of something belongs to that range set only, is it not? So I have shown that this set is closed under addition. And secondly, if ax is equal to y, and if I take alpha of y, then it is same as a times alpha of x. Hence it is closed under scalar multiplication. Hence is a vector space by itself. Hence is a vector space by itself, and hence a subspace of Rm. Okay. So therefore, other way of saying this same thing is Ax equal to B has a solution if and only if B belongs to range space of A. Because if it belongs to range space of A, then it can be obviously expressed like this. On the other hand, so to the contrary, if B does not belong to, B cannot be expressed as a linear combination of A cannot be expressed as the product A times of X. No, if it cannot be expressed as a product A times of X, then what does it mean? It means it's not in range space. So if it is in range space, it can be expressed as Ax is equal to B, which means that the solution, the problem has a solution. And conversely, if it cannot be expressed, then this problem does not have a solution. Therefore, Ax equal to B has a solution if and only if B is in the range space of A. If there is one solution, there could be even more than one solution, or there may not be. The solution may be unique. That's a different problem. The uniqueness of a problem solution is a different problem from existence of a solution. So this is usually told in engineering, mathematics, and many other places as consistency condition for linear system of equations to have a solution. What is it? Rank of A should be equal to rank of A comma B. So what it means is, see, if rank of A is same as rank of A comma B, then it means that B can be expressed as a linear combination of the columns of A, which means that B can be expressed as Ax is equal to B, which means that the problem linear Ax equal to B, the linear system of equations Ax is equal to B has a solution. On the other hand, suppose the B vector cannot be expressed as the combination of linear combinations of A, then Ax equal to B does not have a solution. This also means that B is linearly independent of the columns of A. So if I consider a augmented matrix A and then the column B, then its rank will be one extra linearly independent vector has been added. So if rank of A is R, then in this case rank of A will become R plus 1. Why? Because it is not having a solution. If it is linearly, if rank of A is R and rank of A augmented B is also R, then it means that B can be expressed as a linear combination of A, and therefore it has a solution. On the other hand, if rank increases by 1, which is to say that B is linearly independent of columns of A, then Ax equal to B cannot have a solution, because if you assume that it has a solution, then it means that A, B, so that is x minus 1 will go to 0, which basically would mean that this is a linearly dependent set of vectors, because this is a non-trivial vector which takes it to 0, but that opposes the requirement that it is linearly independent. So treat this is how usually we discuss a linear system of equations in a first course in engineering, usually the consistency theorem. But these are very intuitive concepts, but no doubt important concepts. Now suppose that the a rank of A, this is a M cross N matrix, and all the columns are not linearly independent, are not linearly independent, which is uh, to say that uh, rank of A is less than N. For example, suppose I take 3 cross 5 A as a 3 cross 5 matrix. Then the rank of A is less than or equal to 3, because I already told you that it is the maximum number of linearly independent rows or columns. Since the maximum number of linearly independent rows are 3, so rank of A will be always less than or equal to 3. So therefore rank of A is always less than N, which means that these 5 columns will always be linearly dependent. So therefore in such a case, such a rectangular matrix, uh, I will find that Az equal to 0 will always have a solution with Z not equal to 0. So suppose I have Az1 going to 0, I have another Az2 going to 0, then A alpha 1 Z1, where alpha 1 is a and alpha 2 are scalars, A alpha 1 Z1 plus A plus alpha 2 Z2 will also go to 0, because A times of Z1 goes to 0 and A times of Z2 goes to 0. So this will always go to 0. So therefore, this means that all these null space taking vectors, constitute a vector space which is called as null space of A. So I'll give you one example. Take a very simple matrix A. A as 1, 1, 1. Okay. Now, so if I say Az to 0, then it means Z1 plus Z2 plus Z3 should be equal to 0. So you can take 1 minus 1, 0 as one set, 0, 1 minus 1 as another set, and then generate as many as you want out of this. So the moment you say something is a vector space, and this is actually the null space is a subspace of what? Is a subspace of Rn, because it is relating to the x vector which maps after pre-multiplication by a to 0 vector. So then the subspace will always have a dimension, and therefore the dimension of null space is going to be less than n. The dimension of the null space is going to be less than n. In this case, the dimension of the null space is 2. In this particular case, the dimension of the null space is 2. And what is the dimension of range space here? The dimension of the range space in this particular case is only 1, because x1 plus x2 plus x3, a times of x is just a real number, so it comes from just an r1. So therefore its dimension has to be 1. So what did you get here? Dimension of null space, which is 2, plus dimension of range space, which is 1, is equal to 3, which is max of m comma n. If A is a square matrix, if A is a square matrix, then dimension of the null space I will show by calligraphic of A, plus dimension of range space, which I will show by calligraphic R, will be equal to n, and this is what is the famous rank-nullity theorem of linear algebra. Okay, now let's say let me for the time being now restrict to n cross n matrices. Then Ax is equal to B. Okay, suppose I am suppose suppose uh, okay, I'll just put it very simply. I'll put it this way: if dimension of null space is 1 or more, that means there is a non-trivial null space is 1 or more, then if Ax equal to B has a solution, then it has infinitely many solutions. So simple. If it has a solution, then it means there is some x1 which goes to B. Now, because the null space is non-trivial, there is some z vector in, take some null vector in the null space which is not 0. Then Ax1 plus alpha z is also a solution for all alphas, because Ax is equal to Ax1 is equal to B and Az is 0. So therefore it will always have infinitely many solutions. If dimension of null space is 0, if the dimension of null space is 0 and Ax equal to B has a solution, then it must be unique. Then it must be unique. Why? Because suppose to the contrary, suppose to the contrary, Ax1 equal to B, Ax2 is also equal to B, x1 not equal to x2, then ax1 minus x2 will become map to 0, such that this will be a z vector which is not equal to 0, which means az is equal to 0, z not equal to 0, which means dimension of the null space of A will be greater than or equal to 1, which is a contradiction. So now if A is a square matrix, Ax equal to B has, and rank of A is n, rank of A is n, then by dimensionality of by the rank nullity theorem, dimensionality of the null space of A will be 0, because the range space has, what is the dimensionality of the range space now? Now the dimensionality of the range space of A is n, because A has n cross n matrix, it has all linearly independent vectors, so it can span the complete Rn. The Rn is in the range space and nothing can be bigger than Rn. So therefore the range space dimensionality is n, but dimensionality of range space plus dimensionality of null space has to be equal to n. So dimensionality of null space becomes 0. So therefore if rank of A is n, or the matrix is non-singular as it is said, then every Ax equal to B has a solution and it is unique. So therefore we write X is equal to A inverse B, because now our 1 1 and onto mapping conditions are fulfilled. 1 1 and onto mapping conditions are fulfilled when we look at this as a transformation, pre-multiplication by A as a transformation. We see that 1 1 and onto conditions are fulfilled, and therefore you can, given a B vector, there is a unique vector X which you can associate it with it, which is the inverse operation, and hence A inverse exists, and therefore the matrix is invertible. So therefore, I always use this, and many people use this. Singular matrix implies zero eigenvalue, at least one zero eigenvalue. And non-singular or invertible matrices means all non-zero eigenvalues. And if all of these eigenvalues are greater than 0, then we said that the matrix is positive definite. So I think today we got some introduction to the range space and the null space of the matrices. So actually we did not start with QR decomposition. So I am going to rewrite this as, probably a good title would be rank nullity theorem. You got idea of uh, uh, you got an idea of the range space and the null space of the matrix. Just 1 minute. Rank nullity theorem, I'll say, and I think I should say this as a review of the I should say this as review of the rank nullity theorem. So we will yeah, finally I got it what I wanted. Review of rank nullity theorem. We will stop here and I'll come back to you tomorrow with either QR decomposition, or we are actually also now reaching a launch point for linearly constrained optimization problems. Thank you.